Okay, here we go. So we'll go ahead and test on Wednesday. Let's zip through some of these problems though. Just kind of hit one of each of the different kinds. Okay, so this first one here, and it was requested of me that I put a formula sheet for you on Moodle, which I will do. So I will, I'll do that right after school. It should be up there by this evening. I'll make it a PDF so you can print it if you want to. So let's look at this one now. The formula that goes with this. Who can remember what's the formula for a pendulum that relates period to pendulum?
2 pi square L over G.
That's it. Square root L over G. Very good. Okay. So all we're going to do here then is we want to know if they give us the length of the pendulum, we could calculate the corresponding period. They want to know if we double that period, what would the length have to be in order to double the period, right? So all we're really going to do here is we're going to calculate, let's just call it, how about T1. So our first period, right, when the pendulum is short, is just going to equal whatever we get when we multiply 2 pi times the square root of 8.70 meters over 9.80 meters per second squared, right? And if we do that, we get a number. What do we get? So 2 pi times square root 8.7 divided by 9.8 gives us 5.92 something, right? So that's T1, okay? Okay, so then now we know that T2 is 2 times that, which is roughly 11.84, we'll say, seconds. Okay. And we want to know what is the corresponding length. So now we're going to go back to our equation and solve for L, right? So we'll get 11.84 equals 2 pi times the square root of L2, we'll call it, over 9.80. So what do we do to isolate the L?
Divide by 2 pi.
Yeah, we're going to divide by 2 pi. Good. So that gets rid of the 2 pi. Now what else?
Square both sides.
Square both sides. That undoes the square root. And then last step,
Multiply by 9.
multiply both sides by 9.8. And so that solves for L2. And that makes sense?
Yeah.
Okay, so what do we get? Let's see, so 11, now I'm going to use the unrounded version, right? So we're going to get this guy times 2 divided by the quantity 2 pi is that number squared is that number, right? Times 9.8. Okay, 34.8. Interesting. Notice anything about that? And the units would be meters, wouldn't they? Okay, 34.8. Is that related to, how's that related to our original? 4 times bigger, okay? We probably, not probably, we knew that had to be that way, right? Because would you agree that everything's a constant here in this equation except T and L, right? So T is proportional to the square root of L. So in order to double T, How much would L have to be increased by, being it's inside the square root? 4, because the square root of 4 is 2. Does that make sense? Okay. So yeah, we could have, if we were really tricky, we could have gotten it without even doing any work. Yeah. Yeah. Okay, zipping ahead. I'm gonna skip this one. I already tape recorded that one. Let's do this one and whoops. Oh, hang on. Where's the one I wanted to, there's the one I want to do right there. Is that a good one?
Sure.
Okay. So a 74.5 kilogram swimmer jumps off an 8.2 meter tower into a deep pool. The swimmer comes to rest 2.7 meters below the water's surface. The net force exerted on the swimmer by the water is what? Okay, so now let's think of it this way. Once the swimmer hits the water, what's the only force acting on the swimmer at that point? We're assuming that that the buoyant force, I guess we do need to make there's one little piece of fine print. When you're in the water, you essentially just kind of float, don't you? Right? Your buoyant force, for most people, it's, the buoyant force just about compensates for gravity. Right? So when you hit the water, we'll assume that buoyant force is counteracting gravity. What's the only force acting on you then when you hit the water? What is it?
I was gonna say how fast you would.
Well, okay, yeah, that's different. Yeah, you're right, different kind of thing. Apples and oranges there. But obviously there's a force acting, and there is. If you dive into a swimming pool, don't you feel some kind of a force when you hit the water? Yeah, so it's a fluid frictional force is really what it is. You're right. So the water is pushing against you, but the water decelerating you is the only force acting, really, isn't it? And then once you come to rest, you just kind of float there, right? You might very slowly accelerate to the top or something, but we'll ignore that part, right? So then if we were to draw a free body diagram inside the water, so let's divide this into parts. Part 1 will be in the air. Part 2 is in the water. For part 2, the only force acting is going to be the force of the water, which is kind of a frictional force, we'll say, right? Agreed? So the net force then is what in the water? There's only one force acting. Right? The net force is the sum of all the forces acting on an object. Well, there's only one of them. So it's just, that's it, right? The net force is just the force of the water. Newton's second law tells us that net force equals what? F equals ma. And really when we say F equals ma, we mean F meaning net force equals ma, right? So then this tells us that the water's force, whatever that is equal to ma. Right? Okay. Well, in order to calculate, so we know water force equals net force, which is ma. I know the swimmer's mass. What do I need to calculate in order to find what the force of the water is then? Acceleration. Yeah, right? And we're given enough information here that we should be able to solve that kinematic equation. So if we go to part 2, what are the kinematic quantities that we know? So when you hit the water, okay, so we know that the displacement is negative 2.7, agreed? Okay. Okay, what else? Okay, but for that's part 1 though, is part 2 is only when we hit the water and start to decelerate.
Your final velocity.
Okay, final velocity is
0.
0, yeah, right, comes to rest. So V is 0. That's all we're given directly, isn't it? We need a little bit more. But what could we probably get from part 1?
The starting velocity.
Yeah, we'd know how fast he hits the water, right? And that's going to be the initial velocity for part 2. Well, for part 1, that's going to be the final velocity, isn't it? In part 1, the guy just drops off the platform or diving board or whatever it is, and there's only one force acting, which is what? Gravity. Mg, right? Does that make sense? Okay. So he's accelerating towards the pool. We know the acceleration then, don't we? A is,
9.8.
well, negative 9.8, right? What else do we know? Initial speed, initial velocity, 0.
8.2. Initial distance.
Okay,
Initial position.
the initial position is
8.2.
8.2, final position is 0. So we could even make that a displacement, right? Displacement's always final position minus initial position. So the displacement we can think of as how far was he displaced? How far did he move during part 1? It'd be negative, wouldn't it? 'Cause it's going down. Good. So we could say delta D equals negative 8.2 meters, and we're trying to find V naught, right?
Final.
Or V final. Agreed? Okay. So we could get that from the non-T equation, couldn't we? So we know we've got the equation V squared minus V naught squared equals 2A delta D, right? So V naught is 0, so we can remove that part of the equation. Right? And now we're just solving, well, that's supposed to be squared, whoops. So we're just solving for V. So V is just the, if I square root both sides, V final is just the square root of that stuff, isn't it? Right? So V for part 1 is equal to the square root of 2 times negative 9.80 times negative 8.2, right? Which is what? Something. Okay, so that is square root 2 times negative 9.8 times negative 8.2. So about 12.7-ish, right? Okay. So the final velocity of the first part becomes the initial velocity of the second part, and that allows us to solve for A, doesn't it? So what's the equation we're going to use then? Yeah, same one, no T, right? So we'll do the same thing. V squared, how do I keep doing that? V squared minus V naught squared equals 2A delta D. We're solving for A, but we know that V final is 0. So that one goes away out of the equation. To solve for A, just divide each side by 2 delta D, right? So A equals negative V naught squared over 2 delta D equals negative 12.7 squared over 2 times negative 2.7. So what do we get? So there's our 12.7 unrounded. Let's use that. Negative 12.7 divided by, well, square it, whoops. Squared. Divided by the quantity 2 times negative 2.7 gives us about 29.8. How many? I think we only got 2 sig figs, didn't we? Well,
3. Oh, 2.
Is it 2?
Yes.
Okay. Yeah, we got 2. So it's 30. Okay. Oops. Well, actually, we're not looking for acceleration though, are we? We're looking for force, right? So the acceleration was roughly 30 meters per second squared. But what we're really trying to do is find the force exerted by the water, which is MA, right? Does that make sense? And the mass is 74.5. So really, and I should have put the M out front, but the mass is, wasn't it 74.5 we said? So now, one last calculation here. So we get this number times 74.5 kilograms is, to 2 sig figs, about 2,200 newtons is the force exerted by the water. Okay? Make sense?
Is that a lot of force for a human to be able to withstand?
No. No, not really. No, that's no big deal. Seems like a lot, but the force is spread out over, on everybody. That's not that big a deal. It looks like a big number, doesn't it? Yeah. Okay, moving on. Questions on that? Okay, good. All right, so what about this one? Let's do some friction ones. Okay, the friction ones are just a little bit different here. Free body diagram, I'd say, is pretty important on the friction ones. Okay? So we're driving along in our car at a constant speed, slam on the brakes, and slide to a halt. So once we're sliding, what are the forces acting on the car?
Friction?
Friction acting horizontally, and that's the only horizontal force, isn't it? Right? What about vertically?
Gravity?
Gravity down,
Normal?
normal force up. Okay, so our free body diagram then just looks like this, doesn't it? We've got frictional force, normal force, mg. So is the car accelerating horizontally?
Yes.
Yes, it is, right? And it has to, because there's only one force acting horizontally, so there certainly is a net force. Is the car accelerating vertically? It's not, is it? Right? The car is sliding across the flat ice. It's not accelerating up into the air, and it's not accelerating, burrowing down into the ice, right? Makes sense? So it's just staying in the horizontal plane. So yeah, it's got no velocity, constant zero velocity vertically. So there is no vertical net force. So what does that tell us about the relationship between normal force and mg? They cancel. They're equal to each other, aren't they? If we wanted to write down, we'll be doing a lot more of this next chapter, but if we wanted to write down what we might call the equation of motion vertically, we would just get, well, the net force, there's a positive force upward, the normal force, and a negative mg because it's pointing down, and that's equal to what? Zero. The net force is zero, isn't it? It's not accelerating. So therefore, normal force is equal to mg, but we can just see that from the free body diagram too, can't we? Right, and that's how we've mostly been doing it, okay? All right, so normal force equals mg. Now, horizontally, there's only one force acting. We know that the net force is just the frictional force, right? And so that's equal to ma, because there is a net force there, right? F equals ma. That's Newton's second law. Net force equals ma. Okay, but what can we do with that? Well, what's our equation for the frictional force? Say it again.
The normal force times the coefficient.
Times the coefficient, right? Mu times normal force equals ma, but we know that the normal force is same as the weight, right? So this is the same thing, I should probably put a K there because it's sliding, right? So mu sub K times the weight equals MA. Right? Okay, so algebraically, anything we can do there to make things simple? Yeah, couldn't I divide both sides by M? Now that's kind of cool. What does that mean physically if I can divide away the mass out of the equation? It disappears completely.
Besides them, what is it?
Doesn't matter. It's the relationship, the acceleration that we're calculating is independent of mass, right? Because there's no place to put the mass in the equation. It canceled out. Okay? So that's gone. And there's our answer. The acceleration just equals mu times g. But actually, we're looking for mu in this one, aren't we? I think the problem is asking us to calculate the coefficient of kinetic friction. So then we know that mu sub k just equals a divided by g, right? Okay. We know g. What's g? 9.8. What's a? Well, a, they didn't give to us directly, but we should be able to find it, right? That's just kinematics. What kinematic information did they give us here? Okay, good. So they gave us the initial velocity. That's just v naught, isn't it? Right? What's the final velocity?
0.
0, because it comes to slide to a halt. So v equals 0. They give us a distance, right? So we slide for a distance of 134 meters. So our displacement is 134. Okay. We could also, if we wanted to, we could say d naught is 0 and d final is 134. But we're not given time here, are we? So we're going to want to write it in terms of a displacement anyway, because we're going to end up using that fourth equation, right? So delta d equals 134. And what are we trying to find? A. Yeah. So what's the equation then? We have all this stuff. V equals 0, V naught equals 18.8. Delta D equals 134. A equals what? Well, that's just that fourth equation, right? So, run out of space here. So we get V squared minus V naught squared equals 2A delta D. V final is 0. So if I solve for A, I'm just going to divide both sides by 2 delta D. And I get A equals negative. V naught squared over 2 delta D.
Didn't it already give you the coefficient? Like, wasn't the whole problem?
No, you're trying to find the coefficient.
No, I thought.
It'd be easier if they did, right? A lot of them, sometimes they do, but this is one where we actually have to solve for coefficient. And so I could either calculate this quantity, or I could even just plug that into this equation, right? And get, no matter how you, either way is fine. So if I just plug it in, I get mu sub k equals that, negative v naught squared over 2 delta d all over g. Or I can just get a number there and plug it into the equation, either way. So what's that give us? Hopefully you remember the numbers, because I don't. So let's see, we had the quantity negative, and then 18.8 was the initial velocity, wasn't it? Negative 18.8 squared divided by the quantity 2 times 134 divided by all that stuff divided by 9.8 gives us an gives us mu. Okay, now can mu be negative?
Shouldn't gravity be negative?
Well, G is 9.8, and usually we put in a negative G. But really what this is, mu can never be negative. What this is telling us then is that it's really equal to the magnitude of A over the magnitude of G, right? Because technically, I guess, we could say that, well, the frictional force is, okay, here's how we could square this, if we really wanted to. Because the frictional force is negative, isn't it? Right? See what I'm saying? So when we solve for, this should be, right, does that make sense? This is actually a negative contributor, so when we solve for mu, that's gonna change the sign. But you don't even have to mess with that. Doesn't it just make sense that we just wanna find out, so we could have added this if we want to. We could say that. Which gives us negative outside, which makes it positive. But really, it's just the magnitude of the acceleration divided by the magnitude of gravity. Doesn't that kind of make sense? I mean, if you just think about this intuitively, we talked about the coefficient of friction as being the ratio of the amount of force required to push, slide an object, compared to the amount of force required to lift an object, right? Isn't that kind of what we're doing here, in a way? Right? Isn't this really, I could multiply both of these by m, and that really would just be kind of the ratio of frictional force divided by weight, wouldn't it be, right? See what I'm getting at? We just divided the m's away. Doesn't it kind of make sense that the coefficient of friction is just telling us if we had a much bigger acceleration, we had a pretty small acceleration because the ice was slippery, right? If we'd had a bigger acceleration, the car would have stopped sooner, and that would have made this ratio a lot bigger, wouldn't it? Right? It would have made mu a bigger number, which would make sense, right? A high value of mu would be like 0.85 or something, right? Low value would be what we got, which was like 0.13 or something like that, right? Does that make sense? Okay. Kind of tricky, a little bit. Questions on that?
Can you go over once again why the weight of the car doesn't matter?
Yeah, why the mass doesn't matter?
Yeah.
The mass doesn't matter because when I looked horizontally, the net force horizontally, there's a force acting in the negative direction, and it's just the frictional force, right? So the net force is negative mu mg, because normal force is just mg, equivalent to mg, right? That's equal to ma, right? We always, Newton's second law tells us that F equals ma, and by F we mean net force equals ma, right? So look at that equation then. Negative mu mg equals ma. Well, I could divide both sides by m, and so the masses go away, right? I could have left the masses in there, but I would have just had a mass on the top and a mass on the bottom. Which is interesting, because whenever a quantity cancels in a physics equation, it means it's irrelevant, right? That the answer is not dependent on that quantity. Okay? Make sense? Okay. All right, moving forward. Let's just get as far as we can. How about this one? One more friction problem, and we'll look at other stuff, like tomorrow. You pull a 48.09 kilogram sled across flat snow-covered ground. The coefficient of static friction between the sled and the ground is 0.206, and the kinetic coefficient of friction is 0.084. So a force of at least what will be required to start the sled moving? To start the sled moving, is it sliding when I want to get it going? No. So is it going to be static or kinetic friction? Static. So really, if I draw a free body diagram here, it's looking the same as before, isn't it? It's exactly the same picture. It's that picture, right? There's some, we're trying to push it in this direction, and there's some frictional force that's moving against us. In order to kick the thing free, I've got to provide enough force in this direction to match the static frictional force or overcome it, right? Does that make sense? So then I know that the pushing force has to be greater than or equal to the static frictional force. Okay, so then I have the same kind of thing going on, right? I've just got, whoops. I do. I was doing stuff like this. Did I just delete that thing? I think I did. Oh no, there it is. Whew. There we go. Okay. So don't we know here then that the force, the pushing force is going to have to be greater than or equal to the static frictional force, which is mu sub s times the normal force. But what's the normal force involved if I'm pushing horizontally? Just the weight, isn't it? Right? We've got horizontal forces acting, friction and pushing, and then vertical forces acting, weight, normal force. So they're going to be equal and opposite, right? Okay? So that's how I calculate the answer to part 1. It's just got to be at least 0.206 times the mass, 48.09 times 9.8. Right? Now, once I kicked it loose and it's moving, then it gets a little bit easier, right? Because then in order to keep it moving at constant velocity, my pushing force for part 2 just has to equal the kinetic frictional force, right? Does that make sense? Because then my free body diagram, there'll be 0 net force if it's moving horizontally at constant velocity, right? No acceleration. So then I'd have weight and normal force offsetting vertically, and I'd have pushing force and kinetic frictional force offsetting horizontally, right? So I'd get pushing force just equals mu sub k times mg times the normal force, which is equal to mg. But mu sub k is smaller. That's only 0.084, right? So that's going to be a smaller answer. Okay, now the trickier one, I think, is part 3. Part 3 wants to know how much force must be applied to make the sled accelerate with that acceleration. So what am I doing to this picture to make the sled accelerate?
You're increasing your pushing force.
Okay, I'm increasing my pushing force. Exactly. Good. So now if I want this thing to accelerate, now I do need to have a net force horizontally, right? So what's my net force going to be? It's just going to be pushing force minus my kinetic frictional force, which is just that. Just the answer to part 2, really, isn't it? Mu sub k mg, and that's going to equal, my net force always equals ma, right? So there's my equation. And I'm going to solve for F sub p. That's what we want to know, is what's the pushing force need to be. So what do I have to do to that equation to isolate F sub p? Yeah, just add this term to the other side, right? So I'm going to get pushing force equals ma plus mu sub k mg, right? Does that make sense? So I've really got the answer to part 2 plus the extra force required to make it accelerate. I've got a certain amount of force essentially required just to overcome the friction, and then an extra amount of force required to accelerate the thing on top of that. Okay? Make sense?
On part 2, you don't even have to look at the velocity. Like, does it not matter?
The velocity is irrelevant, isn't it? I gave you information about velocity, but I was really just being kind of tricky. It didn't matter what the velocity was, right? Constant velocity is constant velocity. According to our model, does the frictional force depend on velocity? No. All it depends on is mu and the normal force, which in this case is the weight. Okay. Make sense? All right, so work away on those reviews.